All right, IB Physics. So this is the start of a little mini lab for us and some notes and practice problems on this really inconvenient thing called air resistance. You definitely have a lot of experience with it, but we're going to really understand the physics of it today. So I'd like you to take a little moment and just make a prediction. You can circle this on your notes sheet. You have the picture of this slide. What would happen if you dropped two balls with different masses? What will happen with the heavier ball as compared to the lighter ball? So for example, the heavier ball will have a time to hit the ground that is larger, smaller, or the same as the lighter ball. So will it take a longer amount of time to hit the ground, a smaller amount of time to hit the ground, or the same amount of time to hit the ground? So pause the video, make your predictions, and we'll think about these in a moment. Excellent. So you've made your predictions, and some of these you definitely have some things that are pretty clear, like the heavier ball will have a larger mass than the lighter ball. So they have different masses, and there are probably some other things that you thought, oh yeah, these will be different too, and that's totally fine. But we can go ahead and conduct this experiment, and Kathy and Rich conducted it for us. I know. And we can find out that, in fact, the two balls reach the ground at the same time. What madness! And so we have these two balls. One is lighter, one is heavier. And Kathy thinks that the force of gravity must be acting the same on both balls. Rich says, I don't agree. The metal ball weighs more, so the force of gravity is more on the heavier ball. Think about whom you agree with. Or are there parts you agree with in both statements? And how would you reconcile the fact that both balls hit the ground at the same time? So this is a real puzzling phenomenon. It's something that kind of goes against what our experience shows us in everyday life. So when we drop two balls of different masses, they both hit the ground at the same time. So that means they have to have the same acceleration. If the more massive object is heavier, doesn't that mean that it has a larger force acting on it? Right? Because force, gravity is equal to mass times the acceleration due to gravity, so that would tell me that it would have a bigger force. So why doesn't it have a larger acceleration? How weird, right? Well, mathematically we can actually make sense of this with what we know about Newton's second law. So if we know the force gravity on our elephant and on our mouse, the mouse has a mass of 1 kilogram, the elephant has a mass of 1,000 kilograms, so we can calculate their gravitational forces. We can then also calculate the acceleration that they'll experience. And that's going to be the net force, which for both of them, without air resistance, is just that force of gravity. We can then divide by their masses, and we get that they have the same acceleration. So because their masses are different, that means that this larger net force, or this larger gravitational force, is in fact essentially balanced out by the fact that it's also a larger mass. So we end up with the exact same acceleration. In this case, a rounded acceleration due to gravity. And this is something you've probably seen happen before, maybe in a video like this one. This is linked on Schoology if you want to check it out, where we have a feather and a bowling ball, or a feather and an apple, or a feather and a hammer, or whatever, falling in a vacuum. So we have a very light object and a very heavy object. And in fact, in a vacuum, where there is none of this problematic air, they're going to fall at the exact same rate. The acceleration of the objects is the same. That means that the objects increase their velocity at the same rate, and that means they'll hit the ground at the exact same time. And so you can go check this out on Schoology on the link that's there if you'd like to. So the cool thing about physics is that we're actually going to be able to combine together what we know about calculating accelerations with what we've been learning about finding net forces. So we are going to be using some of our constant acceleration equations, and if you don't know these, you might want to take a little moment to double check that you remember what all the things mean, like v is final velocity, and u is initial velocity, and a is acceleration, and t is time, and s is displacement, or the change in position. So we can use these equations to actually calculate what happens to an object as it's falling, so long as we know its acceleration. So we have a little practice problem here that I'm going to quick set up, and this is just something that's exactly like what we did last unit. And so we're going to go ahead and write down what we know and try solving this. So you can pause the video if you have a good idea of how to do it. If you're not sure, keep on watching and I'll solve it with you. So we have a kangaroo can jump 2.62 meters straight up in the air. With what velocity did the kangaroo leave the ground? Whew. Okay. So let's write down what we know in the problem. And this is one of those problems where you're like, Ms. Getz, I don't know anything. They only told us one number. You're right. But you do actually know more than you think you do. So I know that the displacement of the kangaroo, the height it can jump up into the ground, up away from the ground, is 2.62 meters. That's really tall. That's like a lot taller than you. Wow. Okay. I'm just now scared of kangaroos. So our kangaroo can jump straight up. And I'm going to add in a little picture. Here's my kangaroo. Yeah, that's a kangaroo. Looks kind of like a human. And the kangaroo like jumps up into the air, right? Here's my kangaroo up in the air. And you know the kangaroo will eventually come back down. But this picture is kind of going to help me because I can say, okay, this height is 2.62 meters. What else do I know? Well, if I jump straight up in the air, at the tallest point, I actually know that the final velocity, that's initial velocity, Ms. Getz, the final velocity is 0 meters per second at that tallest point in the air. The initial velocity, that's what they want us to find, so I'm going to write a question mark for that. And then, because I know the kangaroo is on Earth, because, you know, we're all on Earth, I actually know that the acceleration of the kangaroo is equal to the acceleration of gravity, or the acceleration of free fall, which is 9.8 or 9.81, or because I don't have a calculator with me, I'm going to call it 10 meters per second squared. It's 9.81, but 10. It's a good round number. So then I can go ahead and say, okay, well, based on all this information, I need an equation that doesn't have time in it. So that means I can't use the first equation, I can't use the second equation, I can't use the third equation, but hey, this one doesn't have time in it. So that will be a great option for me. So I can go ahead and write that down, that I will be using v squared is equal to u squared plus 2as. So notice I'm writing down the equation that I'm using. I'm also going to solve that equation for the thing that I'm looking for. So I know that this is 0. I'm going to put that in right away. The initial velocity is 0. So that means that I will subtract 2as over to the other side. So negative 2as is equal to u squared. And I'm trying to find u, so I'm going to take the square root of both sides. So we get an equation that says u is equal to the square root of negative 2as. And that negative has me thinking about whether or not I have considered directions. And you know what? My picture doesn't have a positive direction. So I'm going to take a little moment and go, let's consider positive up. This way will be positive. So that means down is negative, which means that this acceleration is negative, and that means the displacement is positive. Okay. And I just noticed that will actually be pretty important here. So we have negative 2 times the acceleration, which is negative 10 meters per second squared, times our displacement, which is 2.62 meters. It's really getting to be an inconvenient problem to do in my head. And that will equal our initial velocity. The negatives cancel out, so I have 2 times 2.62. We do that multiplication first. So that's going to be 5.24 times 10 is 52.4. Yeah, I think I'm right. There's always a chance I'm wrong, but I think I'm right. And the units work out to be meters squared over seconds squared inside, because there's meters on top, seconds squared on bottom. Take the square root of that to get our initial velocity, and we get an initial velocity of 5 point... Nope, that's definitely not 5. That's less than 8, but more than 7. So it's 7 point something. I'm going to call it 7.5 because I'm just guessing. And then our units are meters per second. And so we've solved for the initial velocity. So notice that there was a lot of information that we knew in this problem, like the final velocity is 0 meters per second, the acceleration is 9.81 or negative 10 meters per second squared, that we had to keep in mind. And it was really important for me to double check my directions here, my positives, negatives, in my knowns before solving my problem. And in fact, I probably should have done that before picking out my equation. But this is solving problems using our constant acceleration equation. So again, these are equations that we can use anytime we have a constant acceleration. But in reality is so annoying, gets in the way of all of our fun. Heavier and lighter objects don't fall at the same rate. So we're going to be looking at some data of a tennis ball versus a coffee filter, and really trying to understand what happens with this thing called air resistance. Is real inconvenient. So you've heard of air resistance before, you've definitely experienced it before, and it's that force that opposes motion. It's a frictional force that opposes your motion through a fluid, and in this case, because I'm saying air resistance, it's the fluid of air. You can also experience drag in water, or if you were like in a pool of peanut butter, which sounds horrifying, don't do that. You would also experience a lot of drag from that particular fluid. So we want to do a little investigating about what affects drag. So I've got my tennis ball, I've got one coffee filter, I've got 3 coffee filters. We're going to take a video of it, and oh my gosh, wow, look, I used the video tracking software and made you a graph. You also have this on the next page in your packet, but you don't have to look at it just yet. I'd just like you to take a moment and notice. So here is the tennis ball, these blue dots, these little red dots, this is the coffee filter, and you notice that the tennis ball and the coffee filter look pretty different, right? You can see that the tennis ball just keeps getting a larger and larger velocity because this is a velocity time graph. And we see that the coffee filter starts out getting a larger and larger velocity, though at a different slope, a different acceleration than the tennis ball. But then a little while in, it's kind of levels out. Kind of weird, right? And then I can look at the 3 coffee filters, and again, we notice the same sort of pattern. Tennis ball stays the same, very boring. But the 3 coffee filters fall, speeding up, speeding up, speeding up, speeding up, and then they kind of flatten out and stop speeding up. Interesting, right? So what we're noticing is this thing called terminal velocity. Terminal means last. You've maybe heard the word terminal in terms of diseases, which is unfortunate but true. It's the last disease you have. It means it will kill you. Terminal velocity is the last velocity you'll have, which also could mean it will kill you, but hopefully not. So the terminal velocity is when the force due to air resistance gets so large as an object goes down that it balances out the force due to gravity. And so the force due to air resistance and the force due to gravity are balanced, and so the skydiver is moving at a constant velocity, and that's called the terminal velocity. Oh, I'm going to run out of time on my video. So let's pause here and we'll... So this terminal velocity thing is something that is pretty hard for humans to experience. In fact, you're not going to experience it unless you go skydiving, because humans are pretty massive. And we don't have a super large surface area. But you've definitely seen some things in everyday life experience this terminal velocity. If you drop a piece of paper, you definitely see it falling at its terminal velocity. It stops speeding up and just falls at a constant velocity. So what that means is that the paper, or whatever object, the human, falls speeding up, 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 until it reaches this terminal velocity where the velocity remains constant. So the velocity remains constant, the person still is falling, the paper still is falling, it's just no longer speeding up. So in terms of forces, what that means is at the beginning we have force gravity acting on the object, causing it to fall, causing it to accelerate at the acceleration due to gravity. But then as the object goes faster and faster, eventually we get a large enough force drag or a large enough force air resistance, they're the same thing, you can write either, that the force drag is equal to the force gravity, but it's in the opposite direction because it is a frictional force. And so that means that they add up to equal a net force of 0. So terminal velocity is when we have a 0 net force. One thing to note though is that this part where we're speeding up, where the object is accelerating, there might be some drag force, some air resistance here. It's just smaller than force gravity. So the net force here is some value less than that of force gravity because we do have some air resistance. And in fact, the thing about air resistance is that it's really complicated. But it's something that is really well studied. And in fact, now we have excellent understanding of what causes it. So as you can imagine, air resistance depends on a lot of different things. It depends on the velocity of the object, the viscosity and density of the medium. So again, that's that air versus water versus peanut butter difference. The shape of the body, the shape of the object, and the roughness of its surface. Wow, right? And so we get this equation for force drag or force air resistance where we have rho, that is the density of the stuff, so the density of the medium. V is the velocity of the object, and notice that it's squared, so the velocity of the object matters a lot, like a lot. The faster it's going, the more air resistance it will have. This is something you're probably familiar with if you've ever like stuck your hand out the window of a car while you're driving. Be careful not to hit it against anything, but you notice if the car is moving slowly, your hand doesn't really notice very much. If it's moving faster, you can actually get your hand to act kind of like an airplane wing, and really feel that force drag, that force of air resistance. CD is the drag coefficient. We have some values here of drag coefficients based on the shapes of different objects. So the shapes of different cars, and this is something that is really, really well studied in terms of planes and moving objects like cars, things we care about, like trains, so that we can get a sense of how to reduce the amount of air resistance. And then A is the surface area of the body, or the cross-sectional area of the body. So that means, cross-sectional area is like the surface area that is exposed to the body, or if you do a cross-section, you slice the person in half. Don't do that. But the thing that I do want to note is that you're not going to need to use this equation. I'm not going to say, now calculate force drag based on the velocity of the car is 8 meters per second and it has a drag coefficient of 0.3 and it has a surface area. No, this is for your information. But it could actually be a really great thing to consider in the future for next year if you're interested in stuff that moves and fluid dynamics. This could be a really cool IA to really get deep into force drag. And again, the IA is the lab that you plan yourself. So in today's mini lab, you are going to be figuring out what happens to the air resistance using actual data. So you'll be checking out, how about this guy? You're going to be checking out this mini lab here. And I have the data for you, and notice that I've also highlighted the important information you're probably going to want to use. on these. And so we have our tennis ball in blue on both graphs, they're the same. And then the first graph has our one coffee filter. And one thing to notice is that we have two lines. Here's the first line on the one coffee filter, and then here's the second line on the one coffee filter. Same thing on the three coffee filters down here. And the other thing to notice is that they don't start at t equals 0. So this one starts at maybe t equals 2.05 maybe. And this one starts at t equals 1.9 probably. So that's a little bit annoying. And then the other thing that I wanted to point out to you, so you're going to go through, you're going to think stuff through, you're going to figure out your acceleration. Remember, this is a velocity time graph, so that means the slope of our line on our velocity time graph is the acceleration. You're going to figure out the time that it takes to reach that terminal velocity and the value of that terminal velocity. What is that fastest velocity the object can get to? And then the thing that I think will be the biggest struggle is this last part, where you are going to draw free body diagrams. That part won't be too bad, at these two specific times for each object. So the tennis ball will be very easy. You'll figure out why. And then the coffee filter and three coffee filters, where I'll actually have one where we have the object accelerating and one where we have the object in its terminal velocity. And then you're going to try solving for the force due to air resistance. And so that's where having your free body diagram really carefully drawn is going to make your life a lot easier. And really, I wanted to point out that you only need to mathematically calculate 2 of these. 4 of them you do not need to calculate, but 2 of them you will be able to. You will need to calculate. And I do have your masses here for the situation. And so remember that you're going to use Newton's second law. F net equals ma. You know the mass of the object, and you know the acceleration due to gravity, so I think you'll find this challenging, but in a good way. And then as you continue on, this is a pretty easy practice, and then the IB problems are IB problems, so they're pretty challenging, but I do want you to give them a try. Even if you don't get a perfect answer, that's okay, just give them a try. And that is your final required practice assignment. The next assignment is in fact optional, and it's a bunch of quest practice problems that are also on Newton's second law of motion. So good luck.